In fluid mechanics, viscosity matters to us because it ends up playing a big role in the behavior of the flow, in particular whether it's going to become turbulent or not. Viscosity itself is not a difficult concept to grasp. Let's check it out together. Simply said, viscosity is the stickiness of the fluid. We write it with a Greek letter mu, and we define it with this equation here, which is not easy to begin with. Usually we add insult to injury by saying it is a ratio between shear and strain rate, which does nothing to help. But actually, it's important you have a very clear understanding of this definition, and so we're going to unpack it together step by step. Imagine, if you will, a brick of fluid inside the fluid. This brick has a thickness delta y and an area A, and we're going to perform a little thought experiment on it so we can measure the stickiness, the viscosity of the fluid. What we're going to do is we're going to apply a force. I'm going to pull on the top surface like this towards this direction. And as I pull with a force F, the fluid brick is going to deform, it's going to strain at some rate. Yes? And this is going to result in the top area having a higher velocity, delta V higher, than the bottom one. It's going to strain like this. At this point, it's important that you see the difference in behavior between the fluid and the solid here. If this were a solid, then I would apply a force, but it would not move. It would just deform like this. And if I were to release the force, then the solid would spring back into its original shape. Not with a fluid. With a fluid, keeping it in shape does not require a force. And if I apply a force, the movement, the deformation is going to remain constant. It's going to continuously deform to infinity. I think you can have the intuition in this thought experiment that the force F is going to depend on a few other parameters as the brick deforms. In particular, the force will increase if I increase the top area because I'm affecting a larger amount of fluid. The force will also increase if I increase the velocity. Can make sense? The faster I pull, the more force I will require. The force will increase with decreasing thickness. This is because for a given velocity, the deformation, the strain rate, is going to be much higher if there's a small amount of fluid than if there's a large amount of fluid. And lastly, and this is what we're after, the force is going to increase with increasing stickiness, increasing viscosity. So what we do now with this slide is that we turn it around and we begin with a statement that viscosity is the thing that increases together with the force. And in order to write this as an equation, we need to remove the influence of all the other terms. So we end up writing this equation here, this definition, which is that the viscosity mu is equal to tau, the shear stress, divided by the strain rate, which is delta V delta Y. So let's unpack it slowly. On top, the shear stress is the friction effort, so to speak, where I'm pulling a force divided by an area, F divided by A, tau, the shear stress. And on the bottom is the strain rate, which is delta V delta Y, which is the rate at which the box is going to be strained. Yes? Delta V delta Y is an intuitive way to write it, especially when you work with finite distances. But if we were to be really precise, we would say dV dy, or partial V partial Y, a partial derivative of the horizontal velocity with respect to the vertical distance. The unit of viscosity is the Pascal second. Pay attention here, it's not Pascal per second, it is Pascal multiplied by second. And just for information, 1 Pascal second is rather large. It's a rather sticky fluid, like thick oil. Here are the viscosities of a few fluids. On this diagram, the scale is logarithmic at the bottom, which means that every step you take horizontally, you multiply the distance by 10. 10, 100, 1,000, 10,000, and so on and so forth. So it's a bit tricky to read the first time you work with it. I'm using a logarithmic scale here because I want to represent all the numbers at once on the same diagram. If I were to use a linear scale, then the same data would look like this. Yes? And here on this diagram, you have honey at 50 Pascal seconds. It's 100 times more viscous than the next item, which is oil, motor oil over here. And all the rest of the data is squished up against the zero axis. If I wanted to see a bit better what's going on the left side of this diagram, I would entirely remove the honey. And in this case, we would have the motor oil on the right, 5 times more viscous than olive oil on the left. If you want to see more into this, you remove the engine oil and you land on olive oil being about 10 times more viscous than blood, the next item on the list. Remove the olive oil and just look at blood, and you see that blood is about 5 times more viscous than water. Remove the blood now, and you see that water is about 100 times more viscous than air. If we go back now to having all of data at once displayed with a logarithmic scale on the bottom, take a few seconds to observe this diagram, and you will see that honey is about 10 million times more viscous than hydrogen. To get a feel now for viscosity, I've assembled 3 liquids here. On this side here is liquid water at about 1 millipascal second, just ordinary water from the tap. In the middle is a mix of water and glycerine, and this has a viscosity of about 500 millipascal second. And on this side here is pure glycerine, which has a viscosity of about 1 pascal second. And I think just by shaking slightly the jars, you can see already that viscosity ends up having a major role on the dynamics of the flow, on its behavior in general. Interestingly, in the middle, to get about 500 millipascals, so halfway through the both of them, I had to mix 90% glycerine and only 10% water in this jar. So viscosity does not grow proportionately with the mixes. To get a very direct feel now with your hand for viscosity, you can stick your hand inside the jar. But you need to move it. If you leave your hand stuck inside the jar like this, at best you will measure some kind of heat transfer coefficient. You want to move it, but you also do not want to move it sideways like this, because in that case you will apply pressure on the fluid and you'll have a better feel for the density of the fluid. What you want to do is to move it along the direction of your palm like this, inside the fluid. And this you will apply here, shear, strain rate, and you'll have a feeling for the ratio between the two just by moving your hand. Oh yeah, very viscous. A couple more things you should know about viscosity before we move on. The science of viscosity, by the way, is called rheology, and there are many things to discover. First thing you should know is that some fluids have non-constant viscosity, which means that depending on how much you strain them, they're going to exhibit different amount of viscosity. These fluids are called non-Newtonian fluids, obviously by contrast with Newtonian fluids, which have constant viscosity. We usually split these fluids into 2 categories. The first one is shear thinning fluids, which means the more you strain them and the lower the viscosity becomes. One example is paint. Imagine you have a big bucket of paint, you put a stick into it and you stir. You will feel a viscosity that's about the same as thick oil, right? But if you now spread the paint on the surface, you have a very high strain rate, then the viscosity becomes very low and the paint spreads smoothly. Imagine spreading in the same way thick oil or honey on a flat surface would not work the same way at all. The second category is shear thickening fluids, and these have even weirder behavior. An example is cornstarch water. If you take it and you strain it very quickly, you will encounter high resistance, high viscosity. But if you go slow, then it will be very thin with very low viscosity. These, though, are really the exception. And most fluids you will encounter in engineering and practice, in particular water and air, have constant viscosity. They're Newtonian. The last bit of information you should have in mind before we move on is that viscosity is very strongly affected by temperature. With liquids, it decreases with increasing temperature. You may have experienced this in the kitchen already. If you heat up some kind of a sugary mixed syrup of some kind, it will become less viscous, right? And the data for water is that it will drop 2/3 of its viscosity if you heat it up from 0 to 40 degrees Celsius, from some freezing temperature to human body temperature. Quite amusingly, gases have the opposite effect. If you heat them up, they increase in viscosity. The effect is more moderate though, and for air, if you increase it from 0 to 40 degrees, so freezing temperature to human body temperature, it will increase in viscosity by about 10%. All those effects can be quantified with equations and all kinds of models, obviously, but I believe it's best handled by computers. Do not spend much time worrying about it and focus on the dynamics of the flow instead. So let's sum up then. Viscosity is the stickiness of the fluid. We have seen that fluids resist strain rate, not strain. Remember the break of fluid? If you stop pulling, release the fluid, it remains as it is with its weird deformation shape. A solid, by contrast, would spring back into its original shape. Viscosity is how much shear you need for a given deformation rate, for a given velocity differential. And lastly, we have seen that there are vastly different values for viscosity across fluids. So honey is 10 million times more viscous than hydrogen. So that's a good first look, I think, at the topic of viscosity. I hope you'll be able to make good use of it, and I'll see you in the next video. Hi, I am Olivier Klein, and I'm recording a video course in fluid mechanics. If you find this video useful, check out the rest of them at learnfluidmechanics.com. I hope to see you there. Take care.